and welcome to Saturday's edition of Cracking the Cryptic, where today's puzzle was generated by the brain of Apio, one of my favourite constructors. Apio's puzzles are basically, they always have two characteristics. They are always extremely clever and fun, so what more could we want? Now, I know that Apio's been having a tough time recently, so if you're watching Apio, I hope you're feeling better, my friend, and once you start setting again, we will be waiting for those puzzles. Now, on to other things. If you go over to Twitter now, you'll see my response to Mark's solve of Bram Cohen's Three Amigos puzzle last night. Basically, I'm appalled. I don't know what to say. The fact that Mark could solve that without referencing the singing bush is a disgrace. So, @CrypticCracking is our Twitter handle. Go over there and check it out. Other than that, over on Patreon, we've released the solution video to our Hitchhiker's Guide to the Galaxy Sudoku Hunt. That's worth checking out. And we have just received a new, another of these quite brilliant setting videos, this time from ZetaMath. And ZetaMath's put together another absolutely amazing hours worth of content, which we will release on the channel very soon. It might be tomorrow, it might be the day after, but yeah, look out for that. If you've got any interest in setting Sudoku, you will love it. And that's all I've got to tell you about, so let's get on to Apio's puzzle, which is called Regional Differences. And here are the rules. So we've got normal Sudoku rules apply. Along thermometers, digits must increase from the bulb end, so normal thermo rules. Digits along an arrow sum to the digit in that arrow's circle, so normal arrow rules. In fact, not many arrows in the grid, I'm just seeing only two, I think. Digits in cells connected by a white dot are consecutive, and there are only two white dots, so those two digits there have to be consecutive, and those two digits there have to be consecutive. That should tell you something about those three digits together. Digits in cells connected by a black dot have a ratio of 1 to 2. There is only one of those. Each coloured line must contain the digits 1 to 9 once each in any order. So we have extra regions today. Regional differences, that's why it's called this. So these should be 9 cells long. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, and this one's symmetrical. So yes, these orange lines, we've got to put one of the digits 1 to 9 once each in some order. So they don't have to we don't have to go 1, 2, 3, 4, 5, 6 or anything like that. Although that might even work with that sequence of white dots. So, and that's all the rules. So do have a go. The way to play is to click the link under the video. Now I get to play. Let's get cracking. And there is a remarkable lack of digits in this puzzle, or even this must be geometry related, is my first reaction. 1, 2, 3, 4, 5, 6. No, I hate 6 cell thermos because they always look like they might be useful and they rarely are. Because 6 cell thermo, you can still make this as high as 4, 5, 6, 7, 8, 9. So there's basically 3 degrees of freedom. Each cell on this thermo has 4 different options. So I don't really. 1, 2, 3, 4. That's even worse. Yeah, so it must be geometry, mustn't it, that's going to tell us something about this puzzle, because otherwise I've got no clue what's going on. So where does this cell go in box 3, I suppose? Is it locked into anywhere particularly useful? That's the question. The answer is perhaps not. No, actually, look. No, it's not too bad, actually. So if we let's colour this one in. Let's make it blue for a change. So blue can't go in there, and it can't go on its own region because we know there's only one blue along the orange line. So blue's got to be in one of those squares. Blue can't be in its own region, so blue goes onto the arrow in box 3. Now this square, I think, has the merit that it can also be labelled blue, because this one is the same logic. It can't go on its own line, it can't go there, sorry, it can't go there by Sudoku. It can't go on its own line. So it's in one of these 3 squares in box 2. Therefore, it's forced into the same domino as this square. So these squares are forced into that domino in box 3. And that must be symmetrical. Yeah, here we go. Ah, right. Okay, this is interesting immediately. So those squares have the same quality. Don't really like the red though on the with the background of the orange. That I can see a bit better. So and the same, yeah, it's symmetrical at the bottom of the grid. So these 2 squares will have the same property. In fact, yeah, let's think about it a different way, which might actually make it easier to see. Where does that square go on the not between line, on the regional differences line, the extra region line? Where does this cell go? It can't go in those 3 squares, they're in its box. It can't go in those 4 squares, they're in its row. So it's got to be in one of those 2 squares. And the same logic applies, obviously, for the cell that's next to it. So let's use purples for those. And there we go. We've got a little bit of geometry to kick things off. Oh, this isn't Fistimofel, is it? Hang on a moment. Is this Fistimofel? I'm just noticing I've got stuff going on in the 2x2s in each corner. And oh, this could be Fistimofel. 1 second. Let me just have a think about this. So Fistimofel, obviously, if you're not familiar with Fistimofel, basically that's saying that ring there, 16 cells in that ring, contains the identical digits to these 2x2s in all of the corners. And I won't prove it unless I can see a reason to, but let me just stare at it for a second, if you don't mind, just to see whether or not I can see why, or whether this does anything. So what we're saying is that yellow, blue, green and purple have to appear in the ring somewhere. Yellow and blue can't obviously appear in those squares because they're ruled out by these dominoes. So yellow and blue have to be in those squares. I'm not seeing anything. If we knew these weren't yellow and blue, or actually maybe it's better if we do know. If these had to be yellow and blue, then we would lock yellow and blue into these squares on the other. I'm not sure about this. I'm certainly not seeing anything instantly obvious regarding Fistimofel. Let me just think about this. Sorry, I realise I keep saying that, but it's because I can't think of anything sensible to say. Come on. Apio is the El Guapo of this video. And I need the help of the invisible swordsman. Now, come on. How do we do this? What can we learn? Maybe none of these squares here can contain... Oh, is it nines? Maybe it's nines. Nines in row 3, maybe? 9 can be... 9 is quite restricted in row 3. Because you can't put 9 halfway along a thermo. You can't put 9 here without breaking the run of dots, look. Because then it would have to go 9, 8, 7. And the thermo would break because we'd have an 8 before a 7 on the thermo. So 9 in row 3 can go here. Oh no, it's still got 3 places. Oh, bobbins. Let's just check whether we've got any sort of swordfish mumbo jumbo going on. Oh no, we haven't. Oh, you can't put 9 on the Kropki dot, actually. A black Kropki dot can never have a 9 on it. It's either going to contain 1, 2, 4, 8 or 3, 6. So, no 9. It is almost, there's almost something going on, isn't there? Have we got geometry around this extra region? Let's just check that. Yeah, we do, don't we? So where does this domino go in this extra region? This domino will have to go in those two squares. I'm going to run out of colours here. Can I use orange for that? Is that going to... Oh, it does show up. I can definitely see that. And then presumably this one must map onto those two. Now I really am running out of colours. No, I don't like that. I'm going to have to use red, I think, even though I can just about see it. I think hopefully you guys can see that there is an orange with a red background here. But now hang on, this looks wrong. One of these red squares is at the end of a thermo, one's at the beginning of a thermo. So those can't be the same digit, can they? If this this is a 6-cell thermo, isn't it? So this is a minimum value of 6. If that was a 6, 7, 8, 9, 10 would break, right. So these two, although what we've done with the red dominoes is correct, we can go further. This red cell cannot be that red cell. So this red cell must map to that square, which is interesting. So oh no, I need another colour. Can I use black? Will that show up? I think it will. I can see. That's okay. Right. So, now the other way round with the orange, does that work the same way? The answer is no, because they're not quite far enough apart. Although this is at the end of a thermo, 2, 3, 4. If this was a 5, if this was a 5, 6, 7, 8, 9, it works. Bother. So we can't do the oranges, sorry. Oh dear, I've got a lot of colour and no progress. No actual digit pencil marked in the grid yet even. So we're going to have to think harder. Keep being drawn back to Fistamafel. Maybe if... wondering if I can prove that yellow... Yeah, the tricky thing about all these colours is that I don't know if they overlap. So I don't know whether yellow... There's nothing to prevent yellow from being orange, or yellow to have a common digit with orange, or with anything else. Now if I could prove that either yellow or blue overlap with green or purple, then the Fistamafel ring would become very interesting, I think. Yellow is the same as... Oh, no, there's a simple... right. Gosh, I had not understood that at all. I had not understood this at all. Right. Ow. My second jab yesterday, and my left arm should not be raised that high just at the moment. Yeah, this is very interesting. Yellow cannot share a digit with purple. Oh, this is beautiful. Right, I totally missed this. Right, but this is absolutely beautiful. Look at this. Yellow can't share a digit with purple. Why do I say that? Well, let's imagine that let's imagine this was a 5, and we try and repeat 5 in purple. Then we know this digit's going to be a 5. That means one of those 3 digits is going to be a 5 in column 3. But look what happens by the geometry. We're going to have a 5 in one of these 2 squares, a 5 in one of these 2 squares, because we know purples have to mirror down here, yellows have to mirror up here. Now where do we put the 5 in column 7? Well, it's going to have to be in one of those 3 squares, but that means we've got 2 5s on this sort of rugby post between line. We can only have one of each digit on any not between line, you know what I mean, the regional differences line, the extra region line. So Now that, I think that just propagates that logic. In the sense, what do I mean by that? Well, I think the same thing. If we try and put 5 here, and instead of putting 5 in purple, let's try and put it in green. If you put 5 in green, you're going to get exactly the same effect. Look. You get that. You're going to have to put 5s in both of those strings of digits in there, and that breaks the regional differences line. So now the wonderful thing about this, of course, is that this works for any of these dominoes because the logic is completely symmetrical. So we now know that blue doesn't reappear in purple or green, and that means that these 4 dominoes here, the horizontal dominoes in rows 3 and 7, are 8 different digits. Ah, that's it. And none of them have a 9 on them. Because if you can't put a 9 partially along a thermometer, you can't put a 9 on a 2-cell arrow. It's impossible. So this is absolutely beautiful. These digits are the digits 1 to 8. And you can't put 8 on the thermos, because you'd have to get to at least 10 by the time you get to the top of the thermo. So now I know one of those 2 squares is a 9. That is absolutely beautiful. So this, or this, there's going to have to be a 1-8 pair, because we know one of the horizontal domino cells is an 8. We know that it must go on the arrow, so it must be accompanied by 1. My phone is now going nuts, which is annoying, and probably somebody's ringing me to celebrate the breakthrough for this puzzle. So what does that mean? I'm just wondering if we can do something similar with 7. That's the next question. Let's have a think about this. So this is going to be very awkward to pencil mark, because I don't know which of these is 9. One of them is, but I don't know which one. Let's just make it this one, so we can at least sort of investigate what it might mean. If this is 918, now we've got to put a 7 somewhere. Where are we going to put, when I say a 7 somewhere, I mean we're going to have to put a 7 in one of these cells. Now, good grief, right. Which of those dominoes are we putting 7 into? Because I think the answer is only this one. And if this is the only one that contains a 7, we can't accompany it with a 1 because the 1 has been used, and we know these are 8 different digits. So the 7 will go with a 2, and this would be a 9 as well. Now, why do I think the 7 has to go here? Well, it's because I don't think I can put it anywhere else. If I put the 7 on this thermo, I would have to put it there. And then this would be 8, 9, which will break that. Or, in fact, maybe... Yeah, no, that's good. That's good logic, isn't it? I'm just trying to see if there's a simpler way of doing that, but I can't see it. Now, if I put 7 on this one, on the other hand, it's a bit more complicated. Again, the 7 would have to live here, but because it couldn't go here without making this square a 10. But 7, 8, 9. 9 is in orange, and orange gets reflected on its regional difference line in there and would clash. So you can't put 7 in there, you can't put 7 in there, you have to put 7 on the other arrow, and that logic is completely symmetrical. It wouldn't have mattered if I put the 918 here. I would have reached exactly the same conclusion because it's all symmetrical. So now we know that this is a 9. Now we have got digits. We definitely know these are 9s, but we don't know where the 18 and the 18 and the 27 go. This is either 18 or it's 27. This is either 18 or it's 27. 9 Right, now 9 in the central region can't go on the bulb of a thermo. So 9 is in one of those two cells. This is genuinely fascinating, this puzzle. It really is. It's incredibly clever. And this is why I love Apayo's puzzles. They always have this sort of surprisingly clever twist to them. Now, having said that, I'm now a bit stuck again. What have we got to put on these thermos then? We've used up 1s, 2s, 7s and 8s. So these are 3s, 4s, 5s and 6s. Now 6 is definitely a higher number than 5. So we can't make this a 3. We can't make that a 6. Just looking at the thermo logic, we've got to increase as we move along the thermo. So we can do the same thing here, look. And okay, well that means that, oh, this is going to get complicated again. One of these squares is a 6 now. And look how its thermo is going to behave. There are 2 thermo cells sticking into box 4, 2 thermo cells sticking into box 6. So wherever the 6 goes, it will have to go 7, 8, because it can never get as high as 9 on its thermo. That means there's an 8 in one of these 2 squares and a 7 in one of these 2 squares. And this pencil marking is hopeless, I know, but I'm just trying to understand what's going on. So actually, maybe that's the thing I should do. Do you mind if I'm just going to look at this just so I can see what it does. 8, 7, 6 would remove 6 from there. So then once you remove 6 from there, you remove 5 as a possibility from here. So then one of these two has to be 5. Oh, good grief. Right. Okay, Right, I've got a deduction here that it's complicated. It is complicated. I think it's symmetrical. I think, which is good. Right, but the question I was asking is, once we fix the 6, and we don't know which side the 6 is going to be, it could be here. And if the 6 is here, it would go 7, 8 up here. But once we fix the 6, we then have the question, which one of the remaining digits is a 5? It could be this one, next to the 6, and I think that's what it's going to be. Because if it's not, let's try and put the 5 here and see why it breaks. Because now this 8, look, is looking at this square. And if we'd done it the other way round, there would be a 5 here and an 8 here looking at this square. So it's symmetrical, it is working. But, so how do we fill this thermo? Given this can't be an 8 or a 9, this has to be filled with 6 and 7. But once we put 7 in orange, what happens? The geometry of the puzzle tells us there's a 7 over here by force, because I need to put a 7 in this extra region, and that 7 will clash with the 7 we've put there. So that is, I agree, if you're thinking that's complicated, I cannot argue with you. And I'm not even sure it takes us forward very far, because what it does is it means that wherever the 6 goes, well, yes, whichever one of these is 6, it is surrounded by 5, 7, 8 for certain, which means the other thermo can't have 5 and 6 on it, so that has 4 and 3 on it. Right, what on earth does this mean? That is the question we are wrestling with. So now we've worked out, yes, it is good. It is good because we've worked out 6 is in one of those squares. So, and we've worked out 5 goes next to 6 on whichever thermo it's on. So we know that this square and this square are never 5. And this square and this square are never 4, therefore, because we know the 4 is either here or here next to a 3. One of these is an 8, Oh no, am I going to have to keep thinking this through now? So whichever let's do it again. So let's do it from this way just to convince ourselves it works the other way. So if we go 6, 7, 8 here, then we know that's 4 and 3. So is there a restriction now on the value of this square? This square can't get as high as 7. So this has to now go 5, 6. Oh, that is interesting. I do not know how people get the idea of constructing these mad puzzles. But now we know, because we can't put 7, 8, we can't put a 7 here because it would reflect here. And the same would be true the other way round. If we try and do it the other way round, we're going to get 7s here and a clash here. So this has to go 5, 6. So we now know, let's see if I could just unwind this. I can. We now know that the next cells up the thermo are either 5 or they're 7, and then the next cells up the thermo are either 6 or 8. Now, that means that must go there. Oh, and this one we don't know. But we've now got a 6, 8 red pair in the central rows of the grid, and we need to put a 6 or an 8 up here. I don't know. Well, obviously this can't be an 8, but I think it probably can be a 6. If that's a 6, that would have to be, these would have to be from 7, 8 and 9. Is that breaking this somehow? Yeah, actually, that is it. That's a good point. That's a good point. Yeah. Here we go. This triple now is a consecutive sequence of 3 digits. So it could be something like that. Whoop, not that. It could be something like that. 1, 2, 3. That would work, except it would break the thermo. But actually 1, 2, 3 doesn't just break the thermo, it breaks this. Because this is either 1, 8 or 2, 7. So we know it needs a 1 or a 2 in it. So that's why we can't do 1, 2, 3 here. Now, what I've just been thinking about is I can't do very high digits here either. Because if this is something like 6, 7, 8, I remove the possibility of there being a 7 or an 8 here, which is wrong. And 7, 8, 9 has the same effect. So this also can't be 3, 4, 5. This hasn't got many options. This has not got many options. Actually, I better do it in a sort of structured way. Let's go upwards. 1, 2, 3 breaks that. 2, 3, 4 wouldn't break this if it was 1, 8. So 2, 3, 4 might be possible. Not sure. 2, I can't immediately see why that's not possible. I'll come back to it. 3, 4, 5 breaks that for sure. So we can't start this with a 3. 4, 5, 6 breaks this. So that's no good. 5, 6, 7 would force that to be... That would force that to be 1, 8 again. So hang on. 2, 3, 4 force that to be 1, 8. 5, 6, 7 forces that to be 1, 8. And 6, 7, 8 breaks it because we can't put 7, 8 in. 7, 8, 9 breaks it. We can't put 7 or 8 in. This is beautiful. So this is 5, 6, 7 here. And this can no longer be a 2, 7 pair. Because whether this is 2, 3, 4 or 5, 6, 7, it rules out the 2 and the 7 as options. So this is 1, 8. This becomes 2, 7. Which means those two squares become 2, 7. And these squares become 1, 8. If that's a 3, look, you have to go 2, 1 on the thermo. Which... no, I was wondering if that puts... Well, this Kropke dot now can't be 3, 6. That square can't be a 1 or a 2. It's too far along a thermo. So this this is interesting. Yeah, this square has to be 4 or 8. Just looking at the combination of the thermo logic and the fact that 3, 6 is not possible on the black Kropke dot anymore. And this can't, yeah, so this can't be 1 or 2, or you'd reach a 0 or a negative number in the bulb here. So this must be 4 or 8. This square is either therefore 4, 8 or 2. No, it's not 2. We've got a 2, 7 pair here. This is a 4, 8 pair. This is a 4, 8 pair. Does that do magic for us or not? It's not immediately obvious to me that that's doing any magic. 2, 7 here. If this is 4, this thermo is completely forced. That's got to be a 3, that's got to be a 1. So if that's 4, that can't be a 3. So if that's 4, that's got to be a 6. Oh, I see what we've got to do here. Right, this is clever again. I don't know how many times I've said that in this puzzle, but it's more than the average on a Cracking the Cryptic video, and that is saying something about Apayo's setting skills. If this is an 8, this is a 4. And look what that does. That's going to force this thermo to be, well, let's look at it. That's 8, 4. So that's going to have to be 6, 5 now, because we know that whenever you get a 6, you get a 5 next to it. Now what's that square? Well, that square's only got the option of being 3. It's got to be less than 8, and it can't be any of these other digits. So it's got to be 3. So it doesn't actually matter, I don't think, whether or not this is a 4 or an 8. That's always going to be a 3. And that's, oh, this is beautiful. And that 3 tells us what that square is. That's a 5. Once we know this square is a 5, we know this square is a 6, 7, 8. 8 goes here, 6 goes here, 5, 4, 3. And suddenly, this is awesome, isn't it? Because now I can remove 3 from there, and that becomes 6, 7, 5. And these two squares are a 2, 9 pair out of nowhere. I've got all sorts of digits in the grid and all sorts of geometry going on. Yeah, like green geometry, 5, 6 here means we've got to put 5s and 6s there. And you can see that's got to be 5, that's got to be 6, just using the old powers of green. Now I've got a 5, 6 pair here. So this is a 5, 6 pair by Sudoku of all things. These are 2s, 7s and 9s, I think, just to complete box 1, and that can't be a 9. I've now got a weird 2, 7 pair in this column. So I must need, what, 1s, 3s and 8s into the remainder? Remainder of column 1, that can't be an 8, so that's a 1 or a 3. That one might have a few options. So 6... is now in one of those two squares because we need to put a 6 in orange, and the other is square. So these two squares are from 1, 3 and 6 now, given we've got this square being a little bit limited. 4 and 3 have to go into those two squares in some order. Let's just try and make sure that we've used this. Oh, this can't be a 1. This is on a thermo. Oh, there's probably all sorts of logic like that I'm missing, actually. There's a 7 here. 7 and 2 go in. This square here is on a thermo. It's got to be less than a 3, so that's got to be a 1 or a 2. That reflects over... this reflects over here into this square, which can't be a 2. So we now know the black square is a 1. That gives us a 3 here. That means that these two squares are a 3, 6 pair, obviously. We can see that. We could have seen that from the 1 as well. And this one is fixing the 1 and the 8. numbers. I've got the same numbers in different colours, which is confusing me a bit because that doesn't often happen when you're doing a colouring puzzle. Okay, so have we now done enough that we can start to finish the rest of this off? Don't really know, I have to say. Not even sure I know quite where to look. This square is a little bit limited because that's, see, so this square's on a thermometer, so this is a 1 or a 2. So maybe that's it. Maybe we've got to now focus on thermos and things like that. This square can't be 5, so this has a maximum value of 4. So this is 4, 3. It can only be 3 or 4 because this cannot be a 1. So this has got to be 2 because it can't be as high as 4 now. So that's a 2. And that's nice because that means that's a 1. Don't know if that gives us this digit. I can't quite see. Now 2 must be in one of those squares by Sudoku, which fixes our 2 and 7, which fixes a 9 at the top of the grid, which fixes a 7 here. And 7 must live in that square exactly in box 3. And 9 is, well, 9's in that domino there, look. So let's put that in case, yes, that's good. That gets us a 9 in box 9. Have we put a 9 on this extra region line? No, and I don't know that we know where that 9 goes. So the 9, but the 9 being vertical here places this as square as a 2. Oh, well, we could have done that with that as well. Yes, you're right. Okay, so all of those go in. Now the rest of this box needs to be 2, 5 and 6. So that seems to be a 5. These are a 2, it's a 3, 6 pair here, so the 6 and the 2 can be done. 2s are going to be in one of those squares. So these squares are 2s, 3s and 4s. And well, actually, no, a better question is where does 3 go in box 9? It's got to go here. So these squares are a 2, 4 pair. This becomes a 3, that becomes a 4. That 5 is fixing the 5 and the 6. I'm hopeful. I'm not going to say anything. I'm not saying anything. We're just going to keep plugging away at this, and hopefully we will find a way through it. So this is a 5 here. Now, if we look down this column, we need 1s, 4s, and 8s, which is still looking okay, isn't it? 1s, 4s, and 8s. Have we used up all our thermo? Oh, no, we haven't quite used up this one. Have we used up our extra region lines? Again, not quite. This one is probably worth penciling, isn't it? Because we have got 5 digits on it. We still need 1s, 4s, 8s and 9s. Unfortunately, I think that's... no, that square can't be 4 or 8, so that's just 1 or 9. This square is just 4 or 9, actually. Which doesn't seem to do anything, rather upsettingly. 9 is a bit interesting. This 9 locks a 9 into one of those 3 squares in box 8. A 9 is in one of those 2 squares in box 5. So the 9 in column 5 has to be in one of those 2 squares and therefore has to be here. And these squares are 1s, 4s and 8s. We don't know anything about them. But bar humbug. Now, can we do anything with this thermo? The answer appears to be no. What about this box then? We need 2s, 4s and 7s, I think. 7 here, good. Every digit is like, oh no, broken it. Oh no, I haven't broken it. Oh, that was horrible. That was horrible. I was looking at these 2 4s, thinking I'd broken the puzzle by having a deadly pattern, but look, this one is on a thermo. So providing this, you could almost do this by uniqueness. I think this will have to be a 3 now to force this down to be a 2. Let's hope that happens, otherwise I will have a deadly pattern. Now, let's look at this column where we seem to have to place 1 and 8 in the bottom cell. And these squares here have got to be 3s, 4s and 9s. So the 3 can only go down at the bottom there. Now, what should we do? Those two squares, maybe? They've got to, maybe I should get rid of the colours, actually. I'm finding it quite hard, even harder than usual to scan. These are 4 9, so that becomes a 3. That gets us the 3 and the 6, which is what I was wanting, because now that forces the thermo down to be 2 4 2 4. Thank goodness for that. Now those squares have got to be 5 and something. Can't scan at all. 5s and 6s. Good. 5s and 6s. Which places a 6 here by Sudoku and a 5, whoopsie, and a 5 here by Sudoku. Now this column's probably a bit interesting, isn't it? That's got to have 3s and 7s into it, which means 7 goes here, 3 goes here. This square's now known, in theory at least. That's an 8. 8. Have we used up? We've almost used up everything if we haven't used up everything. What do we need in here? We need to put a 2 in one of those two squares. Don't know if we can do that. Let's get rid of the 9s in those cells and have a look down at the bottom with hoping that this is going to crack. There's a 1 4 8 triple in row 8, so that's a 9. This is a 4. This row still doesn't have a 2 in it, so we can place the 2 and the 2. This square's got to be a 1 or an 8. And this box still needs, what is it? 1 7s and 9s. So the 9 has to go here. 9 4. This is a 1 7 pair, which we can do. 7 1 1 8. This should be 4. Good, no deadly pattern here. Oh, this thermo. Oh no, that thermo doesn't resolve anything. But this one does. So that's the 1, that's the 8, that's the 8, that's the 4. 1 and 4 here means that's an 8, that's an 8, that's a 1, that's a 4, and that is a 1. And we'll click tick, and that is one heck of a beautiful puzzle. My goodness me, Apio, take a bow. That was extraordinary. There was so much in that. The start is to die for. Good grief. These horizontal dominoes are the magic. That they have to all be different. Maybe there was a cleverer way of seeing that more quickly than I did, but it was very, very fine. I mean, it's a beautiful, beautiful sort of embedded piece of logic. And then the fact that you can lock 9s into these squares is not, it's beautiful and not that straightforward. And then, what did I have to do then? I sort of whittled these down. I think maybe it was that. I can't quite remember. But even this was very clever with how it impacted things like the black Kropke dot. There's just so much logic in that. Honestly, I hope you enjoyed it. I hope you got through it. Let me know in the comments. I do enjoy reading them, especially when they're kind. And we'll be back later with another edition of Cracking the Cryptic.